Segment 61A, the thermal equilibrium of passively heated bodies. Earth-like planets and other planetary bodies or small objects in our solar system, for example, reach a particular temperature because of the balance between absorption of energy and radiation of energy. We know from the Stefan-Boltzmann law that we studied before that the flux that an object emits if it's a black body is proportional to the fourth power of the temperature. And we gave some examples of how much energy objects emitted per unit area, depending upon what temperature they had. So the human body, for example, at 300 K emits 460 watts per square meter, but an object that's twice as hot emits 6 times as much energy per square meter per second, about 7.4 kilowatts per square meter. You can get the total luminosity of an object by multiplying its surface area, so over a sphere that's 4 pi r squared, times this sigma t to the fourth from the Stefan-Boltzmann law, and that tells you the amount of energy that emits. So if you imagine putting one of these black bodies in space, what determines its temperature? Its temperature is determined by a balance between absorption and emission. So you can write an equation that relates the power in to the power out. So for an object of some arbitrary size A, the flux that's hitting it from the sun is just the luminosity of the sun divided by 4 pi times the square of the distance times the cross-sectional area of the object, which is pi times a squared. The amount of energy it emits is just 4 pi a squared times sigma t to the fourth. So you'll notice when you look at these two that there's a pi a squared on both sides. It doesn't matter how big the object is, it'll come into the same equilibrium temperature. So you have L over 4 pi d squared is 4 sigma t to the fourth. You can rearrange this equation by moving the 4 sigma over to one side and taking the fourth root, and you have that the temperature of an object is equal to the luminosity of the sun, or the central star in the system, divided by 16 pi sigma d squared, all to the 1/4 power. Since you have that d squared inside and the 1/4 out, this is going as 1 over d to the 1/2. So the temperature of an object in equilibrium drops as about the square root of the distance from the sun. This is why objects that are closer to the sun are hotter and objects that are farther away are cooler, and why there's a zone over which water is between the temperature of freezing and boiling. You can calculate the size of that zone just by exercising this relationship over that distance. So let's use this in a slightly different application, which is we'll design a good spy satellite that we want to hide from a visible telescope and we want to hide from an infrared telescope. I'll ask you about this in class. Another point is about the Earth. The Earth is only illuminated on one side. That's the day side. It radiates on both sides. It rotates every 24 hours. You notice that it gets somewhat cooler at night, but not enormously cooler. And this allows the Earth to be radiating into space in all directions while only absorbing on one side. And this affects the average temperature of the surface by quite a significant amount.